Hello, future engineers. Welcome to my YouTube channel. If you haven't yet subscribed, please do so because that will keep me going and refreshed. This uh, job is very tiring on my part. So, to inspire me, please support my channel by sharing my videos to your friends and to your friends' friends. I assure you that I will upload so many lecture videos and sample problems beneficial to you as students and maybe an instructor in your university. So this is about part 4 of the 3D rigid body equilibrium. So a 2.4-meter boom is held by a ball and socket joint at C and by two cables AD and AE. Determine the tension in each cable and the reaction at C. So here is the given figure. So let's write each tension into vector form, then transmit the components at the line of action at the point where the tension passes through. Then we analyze by writing equilibrium equations. So first for tension AD is equal to magnitude of tension AD times quantity negative 0.8 I plus zero point 0.6 J, then minus 2.4 K over square root of 0.8 square plus zero point 0.6 square plus 2.4 square. So negative 0.8 I, because from A to D it is leftward along X, upward along Y, then backward along Z, 2.4. So simplifying, tension AD is equal to magnitude of tension AD over 13 quantity negative 4I plus 3J minus 12K. Then tension AE in vector form is magnitude of tension AE times quantity 0.8 I plus 1.2 J, then minus 2.4 K over square root of zero point 0.8 square plus 1.2 square plus 2.4 square. So simplifying, tension AE is equal to tension AE over 7 quantity 2I plus 3J minus 6K. Then let's transmit these components at points D and E respectively. Then we put the reaction components at C also in the positive directions for reaction at C. So 4 over 13 to the left, 3 over 13 tension AD upward, then backward 12 over 13 tension AD. At E we have 2 over 7 rightward tension AE, then 3 over 7 upward, and 6 over 7 tension AE backward. Then at C, let's just assume positive reaction components CX, CY, and CZ. So first we set up moment about y-axis equals 0 to relate tension AD and tension AE. So by right thumb rule, this is the positive sense of moment. So 6 over 7 tension AE times zero point 0.8, then minus 12 over 13 tension AD times also zero point 0.8. So those are only the forces involved in this moment, summation of moment about the y-axis. All the rest either parallel or the forces pass through the y-axis. So relating tension AE with tension AD, tension AE is equal to 14 over 13 of tension AD. And if we sum up moment about the x-axis, then we can now solve the tensions. So moment about the x-axis by right thumb rule equals 0. Then it is equal to 3.6. This is the positive sense of moment about the x-axis. So 3.6 times 1.2 minus 12 over 13 tension AD times 0.6, then minus 6 over 7 tension AE times 1.2. So take note that tension AE is 14 over 13 tension AD, simplifying this equation. So 0 equals 3.6 times 1.2 minus 36 over 65 tension AD minus 36 over 35 tension AE, and tension AE is 14 over 13 tension AD. So in this equation, only tension AD is the unknown, so we can compute tension AD using your calculator. So tension AD is equal to 2.6 kilonewtons. And likewise, tension AE is 14 over 13 of 2.6. So tension AE can now be computed equal to 2.8 kilonewtons. Then, to solve for these reaction components at C, Rx equals 0 equals Cx minus 4 over 13 of tension plus 2 over 7 tension AE, and tension AE is 2.8, then minus 4 over 13 tension AD, 4 over 13 of 2.6. So Cx is equal to 0, and Ry equals 0. So we have Cy plus 3 over 13 of tension AD, which is 2.6, plus 3 over 7 tension AE, which is 2.8, then minus 3.6. So solving for Cy is equal to 1.8 kilonewtons. Then Rz equals 0, or summation forces along Z equals 0. So we have Cz, then minus 12 over 13 of tension AD, which is 2.6, minus 6 over 7 of tension AE, which is 2.8. So solving for Cz is equal to 4.8 kilonewtons. Therefore, the reaction at C in vector form is quantity 1.8J plus 4.8K kilonewtons. So that's it for this problem. A 600-pound crate hangs from a cable that passes over a pulley B and is attached to a support at H. The 200-pound boom is supported by a ball and socket joint at A and by two cables DE and DF. The center of gravity of the boom is located at G. So determine, letter A, the tension in cables DE and DF, and letter B, the reaction at A. So let's express the tension in vector form. First, tension DE. So it is 2.8 plus 6, 8.8 plus 5, 13.8. Then going down 16.5 and going forward 6.6. So therefore tension DE is equal to magnitude of tension DE times quantity 13.8I minus 16.5J, then plus 6.6K over square root of 13.8 square plus 16.5 square plus 6.6 square, where 13.8 again is 2.8 plus 6 plus 5. So that's 13.8. Then 16.5 going down along Y, then 6.6 forward along Z. So tension DE is equal to magnitude of tension DE over 75 quantity 46I minus 55J plus 22K. Then tension DF is equal to magnitude of tension DF quantity 13.8I minus 16.5J, then minus 6.6K. It's the same as tension DE, except for the Z component, which is negative. So divide by square root of 13.8 square plus 16.5 square plus 6.6 square. So tension DF is equal to tension DF, magnitude of tension DF over 75 quantity 46I minus 55J plus 22K. So let's transmit these components at E and F as shown. Likewise, tension BH is 3.2 plus 2.8, that's 6 plus 6, 12, 12 plus 5, 17 plus 13, 30. So magnitude is 600 because this is a pulley, small pulley at B. So the weight of the crate is 600. So the tension on this side is also on BH would also be 600 pounds. So the magnitude is 600. Then it is directed rightward 30 feet, then downward 22.5 feet. So that's why in vector form, tension BH is magnitude 600, quantity 30I minus 22.5J over square root of 30 square plus 22.5 square. So simplifying, tension BH is 480I minus 360J pounds. So let's now transmit these tension components and this tension in BH at points E, F, and H respectively. So this is the X component of tension DE. Y component is downward, 55 over 75. The Z component is forward, 22 over 75 tension DE. At F, towards the positive x-axis, 46 over 75 tension DF. Downward on Y, 55 over 75 tension DF. Then backward of 22 over 75 tension DF. Then at H, 480 along X. Then 360 downward along Y. Then we have tension at BC, 600 pounds, 200 pounds for the weight of the boom at G. So that's it. Then reaction components at A, let's assume positive components, AX, AY, and AZ. So first, summation moment X equals 0 equals, by right thumb rule, 55 over 75 tension DE times 6.6, then minus 55 over 75 tension DF times also 6.6 because this is 6.6. So those are the forces involved. The rest either parallel or they pass through. So 600 and 200 and 360 are not involved because we sum up moment about X. So therefore tension DE equals tension DF from this equation. So if we sum up moment about the Z-axis, then we can now compute the tensions. So moment Z equals 0, right thumb rule, 600 times 12, 3.2 plus 2.8 plus 6 is 12. This is the axis, and the positive sense of moment would be in that direction. So 600 times 12 plus 200 times 6, then minus 360 times 18, then minus 55 over 75 tension DE times 5, then minus 55 over 75 tension DF times 5 also. So those are the forces involved. The rest are either they pass through or parallel to the Z-axis. So take note that tension DE is equal to tension DF. So simplifying the constants, 0 equals 1920 minus 22 over 3 of tension DE, this one. And this one combined, we replace DF by tension DE also. So that's the result. Then we can now compute tension DE, which is equal to tension DF, and that is equal to 261.8 pounds. Then for letter B, reaction at A, so we set Rx equals 0, and it is equal to AX plus 40 for 80 plus 46 over 75 of tension DE, then times 2 because tension DE is equal to tension DF, and this is also 46 over 75 tension DF. Then solving for AX is equal to negative 801.1 pounds. Then RY equals 0 equals AY minus 600 minus 200 minus 360 minus 55 over 75 of tension D, which is 261.8, then times 2 because these two tensions are equal and the components are also equal. So solving for AY is equal to 1,544 pounds. Then RZ equals 0. So AZ plus 22 over 75 of tension DE, then minus 22 over 75 of tension DF. Since tension DE is equal to tension DF and these are of opposite signs, therefore AZ is 0. So therefore the reaction at A in vector form is A is equal to quantity negative 801.1 I plus 1544 J pounds. So that's it for this problem. The bent rod ABEF is supported by bearings at C and D and wire EH. Knowing that portion AB of the rod is 250 mm long, determine the tension in wire EH. B. The reactions at C and D. Assume that the bearing at D does not exert any axial thrust. So take note that AB is 250 mm. Therefore, this distance is 250 sine of 30. So this is 250 sine of 30, 125 mm. Then this length horizontal projection along Z of AB is 250 cosine 30. That's 216.5 mm. Therefore, expressing tension AH in vector form, it is up, right, backward. So tension AH is equal to tension AH magnitude times 125. This is also 125. 250 minus 125 is 125 upward. Then minus 216.5 K towards the negative Z direction. Over square root of 125 square plus 216.5 square. So tension AH is magnitude of tension AH times quantity 0.5 J minus 0.866 K newtons. Then we have to apply the component reactions at C. There will be 3 reaction components at C expected because these are bearings. Only at D where there is no X component of the reaction because it is mentioned here that bearing at D does not exert any axial thrust. So that means there is no resistance along the axis of the shaft CD. So we have CX, CY, and CZ, assuming positive. At D, DY, and DZ only. So we transmit the component reactions of tension at A. So 0.5 tension AH and 0.866 towards the Z-axis of tension AH. So moment summation about X0, we can solve for the tension. So MX equals 0. So all this will be not involved, these forces. So by right thumb rule, this is the positive sense. So 400 times 250 mm. Then minus 0.5 tension AH times 216.5. Then this is also minus 0.866 tension AH times 125. So in this equation, only tension AH is the unknown. Using your calculator, we can now compute that magnitude of tension AH, and it is equal to 461.9 newtons. Then Rx0 to solve for Cx. So Cx plus nothing equals 0. So therefore Cx is 0. Our moment dz equals 0 to solve for Cy. So this is the positive sense of moment. So equals negative Cy times 300. Then minus 0.5 tension AH times 350. 50 plus 300. And minus 400 times 50. So solving for Cy is equal to negative 336.1 newtons. To solve for Cz, moment about dy equals 0. So this is positive sense of moment about the y-axis by right thumb rule. So Cz times equals Cz times 300. Then minus 0.866 tension AF for 61.9 times 350, 50 plus 300. And this is the only equation. The rest of the forces are either parallel or they pass through the y-axis. So Cz is equal to 466.7 newtons. Then to solve for, therefore we can now answer the reaction at C. Then in vector form, C is equal to quantity negative 336.1 J plus 466.7 K newtons, because Cx is 0. Then Ry equals 0 to solve for dy. So it is dy plus Cy, which is negative 336.1, then minus plus 0.5 tension AH, then minus 400. So solving for dy is equal to 505.2 newtons. Then Rz equals 0 equals dz plus Cz, which is 466.7, minus 0.866 tension AF, which is 461.9. So that's it. So dz is equal to negative 66.69. Therefore, d in vector form is quantity 502.2J, 505.2J minus 66.69 K newtons. So that's it for this problem. The assembly shown is used to control the tension in a tape that passes around a frictionless spool at E. Collar C is welded to rods ABC and CDE. It can rotate about shaft FG, but its motion along the shaft is prevented by a washer S. For the loading shown, determine the tension T in the tape, the reaction at C. So take note that this shaft, this collar, C is welded to rods ABC and CDE. This one. It can rotate about FG or about the x-axis. So mx is 0. But there is resistance about y-axis, my and mz. And there are 3 reaction components because there is resistance along fg, along x-axis because of this washer S. So there is resistance along y, movement along y is constrained, and along z. So there are 3 reaction components at C and 2 moment resistances at C, about y and about C for moment resistances. So let's apply the reaction components as well as the moment resistances at C. So Cy, Cz, and Cx. Let's just assume positive component reactions, then positive moment resistances along Y and along Z. That is MCZ and MCY by right thumb rule. So these are the positive directions of moment resistances. So if we sum up moment about X, then we can compute the tension. So Mx equals 0. And by right thumb rule, this is the positive sense. So it is 6 times 2 positive, then minus T times 2.4. This is not involved. It is parallel to the x-axis. So 6 times 2 minus T, this T here, times 2.4. So we can now compute the tension in the tape, and it is equal to 5 pounds. Then to solve for Cx, summation forces X or Rx equals 0, then it is Cx plus T, Cx plus 5 equals 0, no more. So Cx is negative 5. Ry equals 0 equals Cy minus 6. So Cy equals 6 pounds. Then Rz equals 0. And we have Cz plus T, Cz plus T, Cz plus 5 equals 0. So Cz is also negative 5. Therefore, the reaction at C, component reaction forces at C in vector form is quantity negative 5i plus 6j plus minus 5k pounds. That's the reaction at C. And the moment reaction at C, so let's solve for MCy first, summation moment about Cy or My equals 0. And we have MC equals MCy. This tension here, if extended, passes through Y. So this has the moment about the Y-axis. So it is equal to MCy, then minus T, which is 5 times 1.6. This T here, the moment arm is 1.6. So MCy is equal to 8 pound-inch. Then Mz equals 0. So MCz equals MCz. This 6 pounds here passes through the z-axis. So this is parallel. So this T has moment, which is also positive. This is the positive sense of moment above Z. So equals MCz plus 5 times 2.4. Nothing else. So MCz is negative 12 pound-inch. Since there's no MCx, the collar can rotate about the FZ axis or axis of the shaft. So MCx is 0. Therefore, MC in vector form is quantity 8j minus 12k pound-inch. So that's it for this problem. The last one in this part. The assembly shown is welded to collar A that fits on the vertical pin shown. The pin can exert couples about the X and Z axis, but does not prevent motion about or along the Y axis. So Y component of force 0 and moment about Y is 0. For the loading shown, determine the tension in its cable and the reaction at A. So let's express first the tension in its cable in vector form. So tension CF is equal to magnitude of tension CF negative 80I plus 60J j over square root of 80 square plus 60 square. So tension CF in vector form is magnitude of tension CF times quantity negative 0.8I plus 0.6J. 6J. So next, tension DE. Let's transmit the components. And tension DE is magnitude of tension DE times quantity 120J minus 90K over square root of 120 square plus 90 square. So 120 upward, 90 backward, negative 90K. So tension DE is magnitude of tension DE times quantity 0.8J minus 0.6K. And let's transmit it at the components as shown. Then at A, we have AX, AZ, MX, MAZ, MAX, MAZ. So AX, assuming positive reaction components, and AZ, there's no AY, as mentioned in the problem. Then we have MAX, about x-axis, positive by right thumb rule, let's assume, and positive about the y-axis, as shown, about the z-axis rather, as shown in the figure. So first, summation moment about the y-axis equals 0. So this is the positive sense. So therefore we have this 1.6 tension, positive 0.6 tension DE times 80, then minus 0.6 tension CF times 135, 45 plus 90. So we can relate tension DE with tension CF. Tension DE is equal to 2.25 tension CF. Then summation forces Y 0 or Ry equals 0. So equals 0.8 tension DE plus 0.6 tension CF minus 480. Substituting tension DE, which is 2.25 tension CF, into this equation, then we can now compute tension CF. So 0 equals 0.8 of 2.25 tension CF plus 0.6 tension CF minus 480. So tension CF is equal to 200 newtons. Then tension DE, 2.25 of 200. So tension DE is equal to 450 newtons. Then Rx equals 0 equals AX minus 0.8 of tension CF, which is 200. So AX is equal to 160 newtons. Then Ry is 0, so Ay is 0. There's no Ay, there's no resistance along Y. Then Rz equals 0, so we have Az minus 0.6 of tension DE, which is 450. So Az is equal to 270 newtons. Therefore, the force components of the reaction at A, or reaction at A in vector form, is quantity 160I plus 270K newtons. Then for the moment reactions, Mx equals 0 equals MAX plus 480 times 135. So MAX, this is the positive sense, plus 480 times 45 plus 90, 135, minus zero point 0.6 of tension CF, which is 200, then moment arm 135 minus zero point 0.8 tension DE times 90, zero point 0.8 tension DE for 50 times 90. So MAX is equal to negative 16,200 Newton mm, or negative 16.2 Newton meter. Then MAZ, that's the positive sense, MZ equals 0, equals MAZ plus zero point 0.6 tension CF times 80 plus zero point 0.8 tension DE, which is 450 times also 80, then minus 480 times 80. So solving for MAZ, MAZ is equal to 0. Since MAY is 0, therefore in vector form, moment at A is negative 16.2 I Newton meter. So that's all for this part.